All right, today we're going to dive into one of the most incredible pieces of biological engineering you own, the human ear. It's this super intricate system that does way more than just let you listen to your favorite playlist. Which brings us to the big question right off the bat.
I mean, that's really the core of it, isn't it? The ear is the ultimate multitasker. It takes vibrations in the air and turns them into the rich world of sound we experience. But at the exact same time, it's giving you a constant sense of balance and where you are in space. So how in the world does it pull off this amazing double act? Well, let's follow the journey of a sound wave and find out. Our journey starts with the only part of the ear you can actually see. Its main job, super simple but absolutely crucial, to catch sound waves and guide them deeper inside. You know, every little part of the outer ear you see here has a specific, really clever purpose. The auricle, or pinna, isn't just there to hang your sunglasses on. Its unique folds and ridges are perfectly shaped to capture sound and funnel it right into the ear canal. This canal is like a corridor that concentrates that sound energy as it travels inward. And get this, it even has its own little security system, earwax. It traps dust and debris, and its chemical makeup can even keep insects out. It's basically a self-cleaning funnel, all leading to our next stop.
Okay, so once those sound waves have traveled down the ear canal, they hit a barrier, the eardrum. But this is where the real mechanical magic of the middle ear kicks in. Its job is to take those faint vibrations and give them a serious boost. So what is the middle ear? Well, think of it like this tiny, air-filled room, a mechanical transfer station, really. It's walled off from the outside world by the eardrum, and on the other side it connects to the inner ear. And inside this little room, you've got the main stars of the show, the three smallest bones in your entire body, known as the ossicles. What we're looking at here is a perfect little chain reaction, kind of like a line of dominoes. When sound waves make the eardrum vibrate, that first bone, the malleus, or hammer, starts moving right along with it. That motion gets passed to the incus, the anvil, which then pushes on the stapes, the stirrup, and the stapes acts just like a tiny piston, pushing against a membrane that's the gateway to the inner ear.
And I have to stop for a second here because this is just mind-blowing. These three bones are incredibly tiny. The stapes, that last one in the chain, is the smallest named bone in the human body. It's literally about the size of one single grain of rice. It's just incredible to think these minuscule little structures are responsible for transmitting every single sound you've ever heard.
Right, so why is all this amplification even necessary? Why is it so important? Well, here's the key. The inner ear is filled with fluid, not air. And if you've ever tried to shout underwater, you know it takes way more energy to make waves in fluid. This is where the ossicles come in and solve a huge physics problem for us. They act like a lever system, concentrating the force from the bigger eardrum onto the tiny surface of the oval window. This bumps up the sound pressure by 15 to 20 times, giving it the punch it needs to get that inner ear fluid moving. Without this, most sounds would just be too faint for us to even notice.
Okay, now we're heading into the inner ear, and this is where things get really intricate. This is the spot where those physical, mechanical vibrations finally get converted into electrical signals the brain can actually understand. And it's here that both hearing and balance are managed.
The best way to get your head around the inner ear is to think of it as having two totally separate but connected jobs. For hearing, you've got the cochlea. And for balance, that's the vestibular system's job. They sit right next to each other, but they do very different, very specialized things.
All right, let's tackle hearing first. The cochlea is this incredible structure shaped just like a tiny snail shell. When the stapes pushes on that oval window, it sends pressure waves rippling through the fluid that's inside this spiral. It really is the body's own built-in microphone just waiting to translate those waves.
So as these fluid waves travel through the cochlea, they make a flexible membrane inside ripple. And sitting on this membrane are thousands of microscopic hair cells. When that membrane moves, the tiny hairs on top of these cells actually bend. This bending action opens up ion channels, creating an electrical impulse. And that right there, that is the magic moment. It's called transduction, where a physical vibration becomes an electrical signal that your brain can finally read.
Okay, so what about that second job? Balance. The vestibular system actually uses a really similar setup of fluid and hair cells. The three semicircular canals are positioned in three different planes, just like a gyroscope. When you turn your head, the fluid inside them sloshes around, bends hair cells, and tells your brain about that rotation. Then you've got the otolith organs. These guys handle the straight line stuff. They have tiny crystals that shift with gravity and acceleration, signaling to your brain whether you're moving forward in a car or up in an elevator.
Okay, so the ear has done all the heavy lifting. It's turned air vibrations into electrical signals. But here's the thing, those signals don't mean anything yet. Not until they reach their final destination and get decoded by the most powerful computer we know. This final leg of the journey, it's all about the brain.
So that electrical signal shoots out of the cochlea and jumps onto this complex neural highway. It's like an on-ramp that leads through several different processing stations in the brainstem before it even gets close to its final destination in the cortex. Think of it like a relay race. The signal doesn't just go straight to the finish line. Nope, it gets handed off from one set of neurons to the next. And each stop along the way refines the information, like comparing signals from both ears to start figuring out where a sound is coming from. And the finish line for this race is right here, in the auditory cortex, which is tucked away in the temporal lobe of your brain. This is where those raw electrical signals are finally understood as speech, as music, as a dog barking, or a person you love's voice. It's where simple electrical blips become the rich world of sound that we recognize.
So you might be wondering, how does our brain pinpoint where a sound is coming from? It's actually got a couple of really clever tricks up its sleeve, all thanks to having two ears. For lower frequency sounds, it calculates something called the interroll time difference, the microscopic delay in when a sound hits one ear compared to the other. For higher frequency sounds, it uses the interroll level difference, which is basically the fact that your head creates a sound shadow, making the sound a tiny bit quieter for the ear that's farther away. It is an amazing, non-stop feat of computer-like calculation happening in your head. So when you think about it, from a simple funnel to a mechanical amplifier, all the way to this sophisticated biological converter, the ear is just, well, it's a marvel. It seamlessly weaves together two of our most fundamental senses, letting us experience and navigate our world in ways we probably take for granted every single day. And all of this leaves us with a really important question to think about. Those thousands of tiny hair cells that make all of this possible, they are incredibly delicate. And unlike a lot of cells in our body, once they're damaged, they don't grow back. In the world we live in, which just seems to get louder and louder, the challenge for all of us is to figure out how to protect this extraordinary system that connects us so profoundly to everything around us.